Good morning, students. My name is Joseph Okoth, and once again, welcome to our lesson today. That is Fleming's right-hand rule, which is also known as the dynamo rule. Now, Fleming's right-hand rule, as written on the screen, it says that if the thumb and first two fingers of the right hand are held mutually at right angle, with the first finger pointing direction of magnetic field, the thumb pointing in the direction of the motion, then the second finger points in the direction of the induced current. Take note of this point here. Fingers are held such that they are mutually at right angle. That means the thumb, the first finger, and the second one are at right angle to one another. That is what we mean by mutually at right angle. Now, in that state, the thumb will point towards the movement of the conductor or the force, the first finger the direction of the magnetic field, and the second finger the direction of the current. Just as indicated on the diagram, the first one, the thumb, shows the motion, the field, and the induced current. It's very important to practice putting the two fingers and the thumb such that they are mutually at right angle. That's when you'll be able to answer questions that are related to this topic. As you can see, mine, the way I've put them, they are mutually at right angle. This is the thumb, the first finger, and the second. Now, on the diagram, as you can see, we have the conductor XY, and then this is the direction of the force, and the magnetic fields are right into the board. So, using the Fleming's right-hand rule, that is placing our fingers such that the thumb, the first and the second fingers are at right angle, then we can predict the direction of the current. We simply place it like this, such that the force is to the left, so you tilt your thumb like that, and then the first finger points at the screen, and then when you do that, the second finger will automatically point upwards, and that will tell us that the current is moving from X to Y in this particular direction. So as you can see, the Fleming's right-hand rule helps us predict the force, the field, or the direction of the induced EMF. We have an example. A square looped conductor is pulled at a speed across a uniform magnetic field as shown below. This is the loop A, B, C, and D. Then this X, marked with X, shows that the direction of the field is perpendicular to the board that we have. Determine the direction of induced current in 1. AB, AD, CD, and also BC. Let us use our right-hand rule to determine the direction of the induced current. Simply place it such that they are mutually perpendicular to one another. Whereas the direction of the force is to the left, so you make sure that your thumb is to the left. Then where's the field? Right inside the screen. And then with that, our second finger points the direction from A up to B. So along that conductor, current is moving from B towards A. Then it comes to the direction to AD, the conductor AD. Now remember our lesson earlier, current can only be induced in a conductor if there is a change in the magnetic field. Now when the loop is moving to the right, then as you can see, this side AD is not cutting through the magnetic field. Therefore, there will be no current induced along AD. Then side CD, as the conductor or the loop is moving to the right, it's cutting through the magnetic field. Again, we will still use our Fleming's right-hand rule to give or to show the direction. Just like that. Then this is, the force is to the left, to the right. Then we have the field perpendicular to the page. Then automatically our second finger is facing upwards, meaning that current is moving from point C to point D. Lastly, BC. Again, as the loop is moving, side BC is not cutting through the magnetic field. So there is no change in the magnetic field. In that case, no current is being induced along the side BC. Next, we look at mutual induction. What we mean by mutual induction? It occurs when change of current in one coil induces current in another coil placed close into it. The changing magnetic flux, and this is the main point here, the changing magnetic flux in the first coil, which we call the primary coil, links to the secondary coil, induces the EMF in the secondary coil. As you can see, we have two coils here. The first one, which we refer to as primary coil, and the second one, which we refer to as the secondary coil. Now, when this switch is closed, automatically current will be flowing in the direction indicated in the circuits. So if you observe from this point, the direction of current here is in clockwise direction, and immediately when it is opened, the current again is induced in the second coil, as you can see. So the fact that current is being induced, we see the deflection of the galvanometer in the secondary coil. This shows us that the change of magnetic flux within the primary coil has induced current in the secondary coil. Remember, there is no contact in between, but the magnetic field produced within the primary coil is what changes, the change in it produces or induces current in the secondary coil. This other side, this is the explanation of what happening in the diagram. When a switch is closed, current in the primary coil increases from 0 to a maximum current within a very short time. The magnetic flux in the primary coil linking with the secondary coil increases from 0 to a maximum value in the same interval of time, inducing an EMF in the secondary coil. Current flows, hence the galvanometer deflects. Another point that I want to make is that current is increasing from 0 up to the maximum. So the increase in current from 0 up to the maximum is what causes the change in the magnetic flux. And that change in the magnetic flux is what induces the EMF in the secondary coil. Further, this is an extension from the first diagram, but this time when we now open the switch, remember, if I can take you back a bit, as you can see here, we are closing the switch. The galvanometer deflects in the given direction. But when now the switch is being opened like that, the galvanometer now changes in the opposite direction. The reflection is now in the opposite direction, as indicated. So likewise from the previous diagram, when the switch is opened, the current in the primary takes a very short time to fall from maximum value to 0. The magnetic flux in primary coil linking secondary also falls from maximum value to 0, inducing an EMF on the secondary coil. Now, what I want to say is that when we are opening the switch, the deflection is greater than when we are closing the switch. What is the difference? When we are closing the switch, the current takes time to build up from 0 up to maximum. And when you are opening the switch, the current takes a very short time to change from maximum value to 0. So that causes more EMF induced when we are opening the switch than when we are closing the switch. What we have is just an explanation of what I've explained from the diagram. In the induced EMF in the secondary coil is higher when current in the primary coil is switched off than when it is switched on, because the current in the circuit takes a much shorter time to die off than build up. The above explanation is called mutual induction. The induced EMF in the secondary coil can be increased by 1. Having more turns in the secondary coil, 2. Winding the primary and secondary coils on a soft iron rod, and 3. Winding both primary and secondary coils on a soft iron ring in order for the magnetic flux in the primary to form concentric loops within it, thus reaching the secondary point. Soft iron concentrates magnetic flux in both coils. That is why it is used. Up to that point again, students, we've come to the end of our lesson. Till next time, thank you for listening. Bye-bye.